I once watched a video about a very special American plane. Fastest in the world. It is almost impossible to shoot down because it could outrun the missiles. That's how fast it is. 3.2 Mach. Now there's a new video about it. Is it a bird? Is it a plane? It's a bird. It's SR-71 Blackbird. Boots on the ground, Rex, the wings in the sky, eyes above, however you call that plane. It's reconnaissance, right? So it's eyes above.
Saapad läikima ja selga digivorm.
It's called the insane engineering of the SR-71 Blackbird. So we will look inside that plane and we will see what makes it so special. I love these topics, I hope you do also. Before we jump into it, I want to thank the Patreons, the people who make it possible for me to do this as a job. I love it so much, I love it, I love it, I love it. Thank you. We have Crimsonier, thank you for becoming a Patreon. We have Sean Persson, thank you for supporting the channel. And finally we have Dova, a name I've said before. You have become a patron before. Thank you for becoming a patron again, my dude. You're amazing. If you feel like supporting the channel, if you like my style, then head to the link in the description below to the Patreon. Pick your tier, anything helps, $1, $5, it doesn't matter. You are helping me big time, thank you. Go and grab an Estonian YouTuber cup and let's watch a damn cool video about the fastest plane in the world. Woo!
Hard to explain the engineering marvel that is the SR-71 Blackbird. A long-range plane capable of flying 26 kilometers above the surface of the planet. So high that the pilots could see the curvature of the planet and the inky black of space from their cockpits. It flew so fast that the engineers had to develop entirely new materials and designs to mitigate and dissipate the heat
so
generated
cool.
from aerodynamic friction.
I want to marry this plane, it's so awesome. Look at it, it looks so beautiful. Whew. Okay, I sound weird. I should stop.
Entirely unique engines were needed to function from 0 all the way up to Mach 3.2, dealing with the myriad of problems like cooling, fuel efficiency, and supersonic shockwaves interfering with airflow.
Fuel efficiency? I don't think that's a thing you have to think about if you're making a plane, the fastest plane in the world. You're not gonna get any efficiency out of that, I think. It's like you thinking about a fuel efficiency in Mercedes G63. I think this is the same. It's not a vehicle you can expect efficiency out of. Doesn't happen. You can expect speed and power and record breaking, but not fuel efficiency.
A plane so advanced that when it detected a surface-to-air missile, its response was simply to change course and speed up. Even though the missiles had a higher top speed, they couldn't achieve the range and high-altitude maneuverability the Blackbird could. This allowed the SR-71 to run hundreds of missions through Vietnam, North Korea, and Iraq without ever losing an aircraft to enemy fire.
Amazing.
Despite multiple
KD, kill-death ratio, 0. Amazing, amazing.
attempts. The entire plane was built around the propulsion system, which alone was a miracle of engineering design. For one, no turbine-driven jet engine can operate with supersonic flow at its inlet. Yet, this plane was powered by the Pratt & Whitney J58 turbojet engine. But get this, off the shelf, these engines could only provide 17.6% of the thrust required for Mach 3.2 flight, a speed which the SR-71 could cruise at for extended periods of time. How on earth did it manage that? In order to achieve those kinds of speeds, a ramjet is typically needed. A ramjet, as you can probably guess from the name, relies on ram pressure to operate. Ram pressure is simply the pressure that occurs as a plane rams itself through the air. So, as the engine moves through the sky, it funnels this high-pressure air inside. Before entering the combustion chamber, the supersonic airflow must be first slowed down. This basically acts like the compressor stage of a normal jet engine, elevating the air pressure before it enters the combustion chamber. Once the air enters the combustion chamber, it is mixed with fuel and ignited. It expands and accelerates once again out of the exit nozzle.
Oh, you compress the air, then you lit it aflame, it expands, and poof, you're going over a speed of sound. I want to be in that plane. I want to go so fast. I want to feel like Sonic in the air. Gotta go so fast. Okay, this is me getting excited about this plane way too much. So if you don't like this, I guess click away, guys. I can't help myself. This is amazing.
No moving parts, this type of engine is capable of flying at speeds far greater than a typical turbine-driven engine. But it cannot start from zero. It needs forward movement in order to achieve the correct compression of air in the combustion chamber. So, they are either dropped from a conventional plane, have a secondary propulsion system, or are a hybrid of a conventional jet engine and a ramjet, which is precisely what the SR-71 used. The turbojet J...
So ramjets can only work efficiently if they are going quite fast. So they cannot start from zero. So you need a regular engine also to get it up in the air, and then you can combust the ramjet engines. Cool, this is a hybrid, but not a hybrid as we think about them today, electronic hybrid. No, this is a very not fuel efficient hybrid, because both of those engines take a lot of fuel.
The A58 engine of the SR-71 is nestled inside the nacelle here. In front and around the J58 is a complicated system of airflow management. These control mechanisms allow the propulsion system to transition from a primarily turbojet engine to a ramjet engine in mid-flight.
You can make a turbojet engine out of a ramjet engine and vice versa in mid-flight. So you don't need 4 engines, you only need 2, and both of them can actually act as turbojets or ramjets depending on what you need to lift up or to go 3.2 Mach into the Soviet airspace, and no missile is gonna catch you because you're so fast. Like Sonic in the space. Welcome, my friends, to the Estonian soldier hat competition. Today we have 5 new points to 5 states. In the last video, California rose to 19 points, which is the 3rd place. 1 more point and it will be in the 2nd place, sharing it with Arizona. Let's see what happens. Alexander Stephens. Saskatchewan. Canada, that's not the US, wait a minute. Canada has 3 points. It will have 4, making it number 1 in the countries list. 4 points to Canada, number 1, leading the competition. UK, pick it up. Oh, you're gonna love this. We have Jason Quenzer. City is called Lincoln, and it is in California. Jason is not a regular person. He's a special kind of hero because he got 2 hats. California with 19 points will rise to 21. 1 more point and it will catch up to Texas. Come on, Californians, you can do it. Woo! 21 points, making it the 2nd ever state in the competition. We have Joshua Black. Oh, Black, what a family name. The city is Bellevue. Bellevue. It's a nice view in Bellevue, Nebraska. 3 points for Nebraska. We have Derek Pulsifer. Orrington is the name of the town. That's in Maine. The rain in Spain stays mainly on the plain, except for Maine, where it rains always in the plain. That was the 2nd ever point for Maine. And finally we have Jeff Todd. Can you guess where the point goes, dude? Ooh, drum roll. Denton, Texas. Yeah, the Cowboys are back, maintaining the 1st place. But Texans, watch out. California is close by. California is climbing. It wants to take over. Texas maintains its lead in the states. The most patriotic state, I would say, and for a reason. Come on, Californians, you can do it. My friends, thank you for getting the hats. You're truly helping me out. You're making me able to do these videos. This directly supports the channel. Thank you. Let's go back to the video.
First, the inlet spike. It is capable of moving forward and back by 0.66 meters. This adjusts the inlet and throat area, which controls the airflow entering the engine. It also keeps the position of the normal shockwave at its ideal position between the inlet throat and the compressor. This is the most efficient position for the shockwave, as it minimizes the energy lost due to drag as air flows over the shockwave.
Wait, I don't know why does the supersonic boom happen? What's with it? Why does it have to immediately explode when something is going over the speed of sound? And like you can see the air shockwave if that happens for a split second. What's the physics behind it? I know some of you guys are very smart and know about this, and I'm too lazy to Google, so please explain it to me in the comments. I would love to know. What's up with supersonic booms?
Inlet spike stays in the forward position until Mach 1.6. After this point, it begins to move backwards by 41 millimeters for every 0.1 increase in Mach number, keeping the shockwave in its ideal position. The inlet spike contains perforations which connect to the outside of the nacelle through ducts. Initially, the airflow will come from the outside in to provide additional airflow to the turbojet engines. But once the plane hits about Mach 0.5, this airflow reverses. As the plane speeds up, the inlet spike develops a significant boundary layer of air. A boundary layer is a layer of very slow-moving air that clings to the surface of objects. By bleeding this layer of slow-moving air off the inlet spike, it frees up a greater area of the inlet area for high-energy, fast-moving air.
This is some hardcore physics here. I mean, it has to be, it's the fastest plane in the world, but still, for me, a plebeian, a soldier, an infantryman, this is like magic. The future is now, guys. Although this is a very old plane, the past is now, but still, for me, the future is now.
And thus improves efficiency. Around the engine, there is a bypass area, which takes air from the inlet and bypasses it around the J58 engine. This air was used to cool the J58, which again improved engine efficiency and allowed the plane to fly faster.
Could I use this system to cool my laptop, because it's overheating sometimes if I edit a very long video, for example 45-minute video, and I try to render it, it freezes and it is so hot. And please, US military, make a system like that for my laptop.
After the air passes the engine, it rejoins the airflow just after the engine afterburner, adding additional thrust as more oxygen becomes available for combustion and increases the pressure through the ejector nozzle. Air got into this bypass area in a number of ways. There was a shock trap, otherwise known as the cowl bleed, located here, which again helped minimize boundary layer growth. There were suck-in doors, located here, which only opened from Mach 0 to Mach 0.5, to add additional air to the bypass for engine cooling. Air from the aft bypass doors, located just before the J58 engine, also fed into the bypass. These, together with the forward bypass doors, which vented to the atmosphere, were used to control the pressure level in the inlet at the optimum level. If it was getting too high, a pressure sensor would trigger the forward bypass doors to open, allowing more air to exit the inlet.
I can only imagine how many sensors this thing needs. It needs to always monitor the airflow, the temperature and the speed, and accordingly to those adjust everything that's going on in the engine. So it needs a lot of monitors for everything. It needs to monitor every little thing around the plane to know how to work the engines. So if one of those monitors goes out, whatever happens to it, the plane cannot go so fast, because the speed depends on every little detail here, every little monitor detail. Ah, love it. Engineering genius.
While the aft bypass doors were controlled by the pilot. These doors played a critical role in maintaining the position of the normal shock wave. If this was mismanaged, the engine would lose control of the normal shock wave and may even spit it out of the intake, resulting in a sudden power loss called an unstart, which would cause the plane to violently yaw in the direction of the faulty engine. If this happened, the forward bypass doors would open fully and the spike would move to the forward position to reduce back pressure and get the shockwave back into its normal position. Besides this bypass area that took air from the inlet and dumped it into the ejector, there were also 6 bypass ducts that took air from the compressor and dumped it directly into the afterburner. These ducts were the primary mechanism that transformed the engine from a turbojet into a ramjet. Afterburners are great. They significantly add to thrust without needing a whole lot of additional weight. They basically just inject fuel into the exhaust of the jet engine and ignite it with whatever oxygen is left to provide additional expansion and therefore thrust, but they are really inefficient. However, as the speed increases, they are the only feasible way to generate thrust, and they do gain efficiency thanks to the forward motion providing the compression of air needed to run them.
So it's crazy, this plane goes so fast thanks to the fact that it can go so fast. It needs to go fast in one direction for the afterburners to work efficiently, and thanks to the afterburners it can go even faster. So it's like a dead circle. It goes so fast because it can go so fast. Love it!
Instead of the turbine needing to be powered to turn the compressor stage. The crazy thing about the SR-71 is that the engineers could have eked out more thrust from this engine to increase the top speed even more. Ramjets can go up to Mach 5, so why did they stop at 3.2? Would they have run out of fuel? Fuel efficiency in terms of cost doesn't mean a whole lot to a military plane like that.
If you go into Mach 5, you're like a meteorite. The tip of the plane would start burning oxygen around it because it's going so fast through the air and the friction would just cause fire.
The military doesn't care about cost, but the more fuel you carry, the heavier and bigger the plane gets, increasing the fuel it uses. There is a break-even point and the plane's range will be limited, but the engineers did manage to fill the plane up with an astounding amount of fuel with some clever engineering. The plane was strictly a surveillance plane, so no internal volume was used for weapons, freeing up space for fuel. You have probably heard that the SR-71 leaks fuel on the runway because there were gaps in the fuselage, but that's a simple fact that ignores much of the engineering that caused it. The SR-71 used something called a total wet wing fuel tank system, which meant that the fuel was not contained within a separate fuel bladder. This was a weight-saving measure. Separate metal fuel tanks would add too much weight, and lighter plastic ones would melt from the intense heat generated from the aerodynamic friction. So, the fuel was contained by the skin of the plane itself.
What?
The engineers applied sealant to every gap the fuel could possibly come out of.
So the plane is filled with fuel. The entire plane is filled with fuel except for the engines and the cockpit. And there's no fuel tank. So whatever you shoot that plane with, it will ignite. Although it's so fast you cannot hit it. So they didn't have to worry about it. Because no one can hit it with anything because it's so fast. You can just fill it with flammables. Jet fuel. It's filled with jet fuel. If you're in that plane, you're in that cockpit, you're filled with the outer layering of the plane and everything else, you know, it's jet fuel just around you. How cool is that? They didn't mention that in the last video. I am bamboozled by this. Bamboozled.
But because the titanium skin of the plane expanded and contracted with every flight, it gradually deteriorated over time, allowing the fuel to leak out.
It's going to leak.
Because of this, the SR-71 had to regularly go into maintenance and have sealant reapplied.
Oh god, I can only metals play around with hot and cold temperatures. They expand, they contract. I can only imagine how many times they have to re-gap the holes and micro holes that form in there. If it goes up to space, it's really cold, comes back down, the fuel is already leaking. Because there's so many screw holes, so many little cracks in the plane where the plates meet. And it's all, there's no protective layering for the fuel, it's just fuel and the plates. It's obviously going to trip out. It is incredible and stupid at the same time to put the fuel like that. I mean, it's an engineering genius, of course, but as you can see, it leaks, so it needs a lot of maintenance, making the plane probably quite expensive to run.
But it usually came back still leaking, just not quite as much. The number of man-hours required to reduce it to 0 was simply too great to fit it between flights. So they just had an allowable fuel leak limit, which looked like this. This plane, like a rocket, was mostly fuel.
Allowable fuel leak drops per minute. Amazing, amazing. Like, it would be too expensive and too time consuming to fully fix those holes every time the plane comes back. So they just allow it to drip. It's like, let it drip. We don't care. We have the money, we have the fuel, we don't have the time. So let it drip. Right wing, 30 drips per minute, it's okay. Left wing, 20 drips per minute, it's okay. 21 drips per minute, no, you cannot go. There's one more drip. We gotta fix that one. Put some super glue and cap that hole. This is funny. This is actually hilarious. How they are okay with this plane leaking fuel and all that it is made out of inside is fuel. So it's leaking itself in the end. You don't find anything else like it.
Its dry weight, depending on sensor payload, was between 25 and 27 tons. Its wet weight was between 61 and 63 tons, making it, by weight, 59% fuel to feed those hungry engines. Even
this plane is over half fuel, 59% fuel. Oh my god. I can't believe it, it's crazy.
then, without the ability to refuel in the air, this plane would have had terrible range for what was supposed to be a long-range spy plane. Range varied greatly. For example, the engines became significantly less efficient when the outside temperature was higher. A fully loaded SR-71 could expect to burn nearly 13 metric tons of fuel, accelerating from Mach 1.25 at 30,000 feet to Mach 3 at 70,000 feet, if the outside temperature was 10 degrees Celsius above standard. That is 36% of its fuel capacity. If it was 10 degrees below standard, the fuel burn nearly halved to 7.2 tons. And of course, the range was severely affected by their speed and use of the afterburner. But on average, the SR-71 had a range of about 5,200 kilometers, about enough.
5,000 kilometers, you don't need any more. Let me tell you, you don't need any more of that. What are you gonna do? You want more? You want 10,000? What are you gonna do with 10,000? You can fly 2,500 and then fly back. Or you can refuel it in the air and fly all over the world. I think this is well over enough.
Enough for a one-way trip from New York to London. Not terribly useful. The US was not going to be landing at their target to hand over a top-secret plane to the enemy.
Oh, okay. I just make a very stupid comment. Yeah, of course, it makes sense that they don't want to lose this plane if the fuel runs out. But still, if US has bases everywhere in the world, 5k clicks, totally fine if your base is kind of close. US has troops everywhere, bases everywhere. Doesn't need to fly that much because the closest allied airstrip is quite close probably to the plane.
However, with aerial refueling, the plane could stay in the air more or less indefinitely, provided there was no mechanical issues. Really, the range was entirely determined by the pilots. The longest operational sortie occurred in 1987 when the US flew the SR-71 from Okinawa to observe developments in the Iran-Iraq War. This mission lasted 11.2 hours and likely required at least 5 aerial refuelings along the way.
From Okinawa to Middle East, that's half of the world. Half the world away. A little bit more on this plane is fully global. It can go around the world if it wants to.
So, if it wasn't the fuel or engines that limited the SR-71's top speed, what did? At Mach 3.2, the nose of the SR-71 reached 300 degrees Celsius, while the engine nacelles could reach 306 at the front and 649 at the back. This is
why is the nose 300 degrees? It's such a small tip and it's slicing through there. It's not like a wall. It should be very aerodynamic, but it's still 300 degrees. Hey, you physics guys, explain this to me, please. Is it the air friction that creates heat?
What truly limited the top speed of the SR-71. Without careful material selection and design, the plane would simply overheat and fail. Even the fuel needed to be specially formulated to get around these overheating issues. It was a specially formulated fuel called JP7, which has very low volatility and a high flash point. This was partially needed because the fuel leaked on the runway, and they needed a fuel that wouldn't ignite or easily evaporate and make.
This plane is 300 degrees Celsius hot on the tip, and below that tip immediately is fuel, because everything is made out of fuel inside. If that fuel leaks, which it does, to the 300 degree tip, it will ignite, igniting the whole plane. Poof! It's gone. Oh my god, this creates a whole new level of problems.
make the ground crew ill. But mostly, they needed a fuel that wouldn't vaporize in the tanks and cause fuel feed and pressurization problems. The JP-7 fuel was so stable that it actually doubled as a coolant for the entire plane. What? The fuel was pumped around the airframe to cool critical components like the engine oil, hydraulic systems.
The fuel itself, which is 59% of the plane, acts as coolant. So you don't need cooling liquid, you have fuel for that. A fuel which is highly flammable, cools your plane. This is cool. If something's cool, then it's this.
And control electronics. When the fuel got too hot, it was simply sent to the engines for combustion. The fuel was so stable that the plane actually needed to carry shots of triethylborane, a fuel that spontaneously ignites in the presence of oxygen, to start the combustion cycle and afterburners. The plane usually only carried about 16 shots of this, so the pilots needed to manage them carefully, particularly when slowing down for refueling and managing unstarts.
So you could 16 shots, 2 engines, so you could only do 8 very fast accelerations to ignite the afterburning fuel again. So you better go fast steadily. If you go slow and you want to go fast again and switch to afterburners, you only have 8 times to do so. It seems totally enough for me, but still, you gotta be careful.
One huge question I had about the SR-71 was why it was painted black. Airliners are all white to reflect heat and prevent the plane from overheating. If that applies to an airliner, why not the SR-71? The SR-71's predecessors were unpainted, which saved weight, and the areas exposed to highest temperatures were painted black. Why was this? Surely black would absorb more heat. The Concorde was once painted blue for a Pepsi ad campaign and had to lower its speed as it absorbed too much heat from the sun. However, the Concorde did not fly nearly as high or as fast as the SR-71, and as the SR-71 rose, the energy it absorbed from the sun dwindled in comparison to the heat it gained from aerodynamic friction. For this, we have to refer to something called Kirchhoff's rule of radiation, which tells us that a good heat absorber, like a black object, is also an equally effective heat emitter. So, the black paint helped the SR-71 radiate heat away from the plane, as it allowed the plane to radiate more heat than it...
I feel like this is a physics lesson for me. These are really cool science facts here. I didn't know black works 2 ways. If it's a hot day, I won't wear black. It's gonna be too hot, but now I know I can wear it because it also cools me down. Well, it doesn't work like that on Earth, but in space it does, I guess.
Gained from the radiation from the sun. These efforts helped to keep the plane cool, but the structure of the plane still needed to be incredibly heat stable. Aluminium is typically the material aircraft engineers turn to. It was used for the Concorde, but as we saw, it too had its speed limited by heat to a much lower Mach 2. Aluminium is cheap, has a great strength-to-weight ratio, and is easily machinable. Titanium, the material that made up 93% of the SR-71, has only one of these properties.
Titanium is very hard. This plane is made out of titanium. Damn. Hey, you didn't want to make it out of depleted uranium? Even more harder? Or tungsten? Why not?
Its strength-to-weight ratio, otherwise known as specific strength, is fantastic. But titanium is incredibly expensive, despite it being the 7th most common metal in Earth's crust.
What?
The refinement process is incredibly long and requires expensive consumables. It's also not easily machinable, as it readily reacts with air when welding or forging, becoming brittle. For these reasons, titanium is rarely used in structural parts in aviation. However, the real benefit of titanium is its ability to resist heat. The reasons for this are complex that we will explore in depth in future. However, the gist is that titanium alloys have incredibly strong bonding within its crystal lattice that resist heat from breaking them apart. Titanium alloys can resist temperatures up to 600 degrees Celsius before their atoms begin to diffuse and slide over each other significantly, allowing it to retain much of its strength even at 300 degrees. It has also very low thermal expansion, so that expansion and contraction we mentioned earlier is...
That expansion and contraction is what makes the plane leak. So titanium is the reason it leaks so little. If it was made out of aluminium, it would leak like crazy. It would all... The plane goes up in the Soviet Union, right? And the Soviet people get like the rain of jet fuel and they know, oh, it's another SR-71. Because it leaks fuel and it rains.
Is minimized, reducing the thermal stresses in the aircraft. But titanium has its limits, and for the SR-71, this was about 3.2 Mach. Today, engineers have made huge strides in material science. The SR-71 used heat-resistant composite materials as radar-absorbing wedges between the structural frame, located in these locations. The manufacturing techniques needed to make composite materials as load-bearing structures did not yet exist, but that has changed. The SR-71 successor, the SR-72, which is now in development, will take advantage of new
There's an SR-72? Baby, sign me up, I wanna see.
high-performance composites, which will allow it to reach speeds up to Mach 6. Many of its engine components will likely be 3D printed titanium with cooling ducts printed right into the part. Its range also won't be determined by pilots, as it will be an autonomous drone. The insane
Autonomous drone going at Mach 6, oh my god. Oh my god, America. How can you manage this? The future is now, my friends.
engineering that makes planes like this possible fascinates me, and I recently watched an excellent documentary on CuriosityStream that details the build process for the world's largest airliner, the A380, chronicling the massive sheet metal cutting machines that cut the aluminium skin, the vacuum molds that form it, and the biggest oven in Britain that locks the shape in place.
I am amazed, my friends. I'm bamboozled, amazed, and excited for the SR-72 and Mach 6. Autonomous, without a pilot.